Today we're going to be talking about the molecular shape and how that might affect the polarity of a molecule. So yesterday we talked about shapes of molecules, about tetrahedrals and trigonal bipyramidals. And what we're going to do today is we're going to talk a little bit about how that affects whether a bond is what we call a polar bond or not. So we're going to talk a little bit about the covalent bond and how the electrons overlap each other, and then we're going to determine from the molecular shape whether a molecule is polar or whether it is what is called nonpolar. So polarity, or whether a bond is a polar bond or a non-polar bond, it helps describe how the electrons are shared between the atoms in the electrons between atoms that are in a bond. So in an ionic bond, we don't really talk about polarity at all, because if you talk about sodium chloride, sodium completely transfers its electron over to chlorine. So you really end up getting Na plus and Cl minus because sodium has lost its electron, whereas chlorine has gained the electron. Okay, so when we talk about a polar versus nonpolar bond, we're talking about the sharing of electrons that only occurs when you're dealing with covalent bonding. When you're dealing with ionic bonding, there is no sharing involved. So in a covalent bond, the electrons are shared. In a nonpolar covalent bond, the electrons are shared equally between the two atoms. However, if it is a polar bond, and a lot of times we take out the word covalent because we know that if it is a polar bond, it has to be covalent. So a lot of times that covalent is just left out. We'll just say it's a polar or a nonpolar bond. In a polar bond, one of the atoms that's in that bond has a greater attraction for the electrons than the other one does. So if you look at, for example, F2, in F2, those electrons in that bond, that's the bond we're talking about. Are those electrons in that bond shared equally between the two atoms, or does one fluorine pull stronger than the other fluorine? And obviously, when we talk about pulling, we're talking about protons. This fluorine has 9 protons. This fluorine has 9 protons. They both have the same number of shielding electrons. Wait a minute, this is sounding very similar. Remember when we talked about sizes and when we talked about ionization energy? The more protons, the greater the attraction. Okay, we're kind of coming back to that a little bit here. These electrons in this bond are equally shared between both fluorines because both fluorines have the same number of protons and the same number of shielding or core electrons. In a bond such as a bond between, let's say, phosphorus and chlorine, in that case, phosphorus has 15 protons, chlorine has 17. They again do have the same number of core electrons because they're in the same 3p orbital. So the electrons we would predict would be more attracted to the chlorine than they would be to the phosphorus because of the greater number of protons. And so this right here would be a non-polar bond because those electrons are shared equally between both fluorines. Here we would consider this a polar bond because the chlorine has a greater attraction than the phosphorus does. And what that means when we come back here and talk about this one's pulling stronger or these are being pulled equally, what that is referring to is the electronegativity. When we talk about electronegativity, we're talking about the ability of an atom in a molecule to attract electrons to itself and can be used to determine what type of bond has formed. The greater the atom's electronegativity, the easier it attracts electrons. So similarly to sizes and ionization energy, we know that as you go across the periodic table, size goes down. Ionization energy goes up. What about electronegativity? As you go across the periodic table, would you expect the electronegativity to go up or go down? And if we think again about attraction, as you go across, the protons are going up. The core electrons are remaining the same. So as you go across the periodic table, the electronegativity, and I'm just going to write En for electronegativity, goes up. Okay? As you go down the periodic table, we know that the size goes up, the ionization energy goes down, and the electronegativity, again, because there's more shielding electrons, so they're being blocked better, the electronegativity also goes down. So the most electronegative element on the periodic table is actually fluorine. Okay, you would think, well, how come it's not helium or neon, one of those two? Because they're the farthest to the right. Remember, it's the ability of an atom in a molecule. Helium does not form bonds. This electronegativity only occurs in bonding. Okay, so helium, neon, those noble gases don't really participate in bonding at all. You can get maybe a krypton to form a bond or a xenon to form a bond, but typically, especially helium and neon, they do not form bonds really at all. And so fluorine is the most electronegative element on the whole periodic table. That means that if you have a bond and one of the elements is fluorine, fluorine is always going to be pulling stronger than any other element. So here, just like how we just talked about, there's an increase as you go from left to right, decrease as you go down. Again, think about ionization energy, think about sizes. The explanation is the same. Okay, so here we can kind of see a chart of this, and here there's really no exceptions other than in that d orbital, but as you go across from lithium over to fluorine, it goes up. That's the value that they use for fluorine. It has an electronegativity of 4. So as you go across the periodic table, it goes up, and as you go down the periodic table, it goes down. Now, the difference in these electronegativities will tell us what kind of bond has been formed. If there is no difference in electronegativity, if both atoms are pulling with the same amount of force, then you've got a nonpolar bond. If they've got an electronegativity difference of up to somewhere around 2, then you do have a polar bond. And if the electronegativity is greater than 2, then you theoretically would have an ionic bond. Now, they're not going to ask you specifically about, what numbers are and things like that, but you should be aware that typically an ionic bond is formed here when we have a metal and a nonmetal. Here, this is a polar bond because they're two nonmetals and they're different from each other. Typically, two atoms that have a different electronegativity are obviously going to form a polar bond. So a couple of ways that they write this. Notice that weird looking symbol up there. What that means is that in this bond right here, because the fluorine is pulling with more strength than the hydrogen is, it's kind of a weird looking S and then a little minus sign on it, showing that these two electrons that are in this bond are more in the vicinity of fluorine, giving fluorine what we call a partial negative charge. And the hydrogen, likewise, because these electrons are closer to the fluorine, would have a partial negative charge. So it isn't like sodium chloride, where you really do have the plus and the negative. We call it a partial positive or a partial negative charge. Okay, another way that I've seen it written is writing a plus sign where the positively charged one is, and that kind of drawing an arrow going towards the direction of the other one. So a plus going like that. So that's a plus sign, and then it's showing the electron is more towards the fluorine side than the hydrogen side. So that's just a couple of different ways that you may see it written on the AP exam. So here's an example of this. Here you can see the electron density is pretty much the same for the fluorine molecule. Here in HF, though, you can see that fluorine is pulling the electrons more strongly towards its side. And then with lithium fluoride, this is the ionic one. That one is pulling the electrons even farther than HF is. So what bond would you expect to be more polar? A boron-chlorine bond or a carbon-chlorine bond? And again, it just depends on position on the periodic table. So if we look at boron, boron is to the left of carbon. So you've got boron, then carbon, then down here is chlorine. Which one's going to have a greater difference in electronegativity between carbon and chlorine or between boron and chlorine. And the farther apart they are, the bigger their difference in electronegativity. You wouldn't have to memorize that, but you should be able to look at boron and carbon on the periodic table and think, okay, boron and chlorine are farther apart, therefore their bond is going to be more polar. Okay, and if we go back to the actual table that shows the electronegativities, that's how we're going to determine whether it's polar or how polar it is. So how polar is the carbon-chlorine bond? Well, chlorine's 3 and carbon's 2.5. What's the difference between those two numbers? 0.5. Okay, what about the boron-chlorine bond? Again, chlorine's 3, boron's 2. What's the difference? 1.0. So which one's more polar? The one that has the greater difference in electronegativity. Okay, so the next one that they show us is P and F or P and Cl. So again, just looking at the periodic table, we should be able to say that P compared to Cl or P compared to F. P is farther away from F than it is from Cl. Mathematically, if we calculate it, 4 minus 2.1 is 1.9 for the PF bond. And then for the PCl bond, it'd be 3 minus 2.1 is just 0.9. So the PF bond is more polar than the PCl bond. Okay, whoa, way too far. So again, which one would have the partial negative charge? Whichever one has the greater electronegativity. So here the chlorine would have it. Here the fluorine would have it. Whichever one's closest to fluorine will have it. Chlorine would have it here. Chlorine would have it there. Now, that is for very simple, just one atom to another. Okay, but when you have bigger molecules, so instead of just like nitrogen monoxide, you would have to, a lot of times you have a lot bigger molecules where you actually have to take into account something more, just greater in complexity. So a polar molecule is now, instead of just like, carbon monoxide, sorry. Put that one back up there. Is that polar? Is that a polar bond and is it a polar molecule? The answer is yes. The bond is polar. Why? Because oxygen is more electronegative than carbon is. Okay, why is it more electronegative than carbon? Not because it's closer to fluorine, which is true, but because although both atoms have the same number of shielding electrons, oxygen has more protons. Because oxygen has more protons, the electrons are more attracted to the oxygen nucleus than they are to the carbon. So yes, that is definitely a polar bond. Okay, is it a polar molecule? Well, sure it is. Okay, why? Well, because there's only one bond in it, and overall, that bond is polar. Okay, now, referring to larger molecules, a molecule in which the center of the positive charge and the center of the negative charge do not coincide is said to be a polar molecule. A key word you can use with that is, I think I spelled that right, but I'm not sure. Maybe there's two M's in there. Not sure. Is asymmetrical. Okay? Either the molecule is symmetrical or it's not symmetrical. So you can have a molecule where all of the bonds are polar, but the whole molecule is not polar. Okay, and we'll talk about what that means. So you can write it like that, and I already showed you that. So polar molecules align themselves with each other. They're attracted to ions the same fashion as above. How can we assign a numerical value how polar a molecule is? By assigning what's called a dipole moment. So dipole moment is something that you very likely will see on the AP exam. If something has a 0 dipole moment or a dipole moment of 0, it means it's nonpolar. If something has a non-zero dipole moment, then it means it is polar. Okay? Whenever two electrical charges of equal but opposite magnitude are separated by a distance, you get this dipole that's established. So again, you can have that partial negative charge and the partial positive charge. Those are two electrical charges that are opposite but equal, and you get a dipole. The measurement of a dipole is called the dipole moment. There's the letter mu, and it depends on the charges and the distance between them. And I'll show you what that means here in just a second. Okay, so if we look here at bond polarity again, we can see that the electrons in a bond are shared between the two atoms, and the greater the difference, the more polar it is. If there are more than two atoms, then the magnitude depends on the polarity of the individual bonds and the geometry of the molecule, or many times what we call the shape of the molecule. So for each bond, we have to consider, number one, whether the bonds are polar or not, and number two, what the shape of the molecule is. So they have magnitudes and they have directions. So let's just get right to it, huh? So using molecular geometry, draw a CO2 molecule and an H2O molecule. So a CO2 molecule has the carbon in the center. It's got a double bond. It's got the oxygen. If we were drawing this, we would put the dots on the outside here just like that. And on an H2O molecule, we would do the same thing. Okay? Then we have to think about the shape. What is the shape of a CO2 molecule? Hopefully you know that that is linear. And an H2O molecule has got two bonding domains, two non-bonding domains for 4 electron domains all total. The shape of 4 is a tetrahedral. You take 2 parts of the tetrahedral off and you're left with a bent molecule. So this one's linear, this one is bent. Okay, couple of ways we can describe this. Is CO2 a polar molecule? The answer is no. It is a non-polar molecule. Okay. Why? Because it is symmetrical. Okay, the oxygens are both pulling with the same amount of force on each side. One's pulling to the right, one's pulling to the left. They've got the 180-degree bond angle. So therefore, basically, both of these dipoles cancel each other out. This one's going this way, this one's going that way. Where is your net center? Right here, right on the carbon. So your center of your positive charges and your center of your negative charge are both centered right on the carbon. So therefore, that is a non-polar molecule. Water, on the other hand, is a polar molecule. Why is it polar? Because it is asymmetrical. Gosh, I don't know how to spell that. Asymmetrical, maybe just one S, so you don't have a bad word at the beginning. I don't really know. It's asymmetrical because where's the center of the negative charge? It's right on the oxygen. Where's the center of the positive charge? Well, here's one hydrogen down here. Here's another one down here. Therefore, the center of the positive charge is right there. They do not coincide. Therefore, it's asymmetrical, which means it's polar. Okay, so if the bonds are canceled out by the equiangular pull of the bonds, it's nonpolar, just like we saw in CO2. Another way to put it is if the molecule is asymmetric, there you go, just one S. One S, two M's, huh? With respect to the outer atoms, then it is polar. So molecules in which the center of the positive charge and the center of the negative charge do not coincide are polar, and they do have dipole moments. So here we've got 5 molecules. Are they polar or nonpolar? So the first thing you do is you just draw the Lewis structure. HCl. Okay, does one of them pull stronger than the other? Yes, the chlorine is very close to fluorine. Your dipole moment would look like that. Is it a polar molecule? Yes. Why? Because it's a polar bond. The chlorine's pulling stronger than the hydrogen. Therefore, it's polar. How about CCl4? Now here we want to think about shapes a little bit. Where we've got 4 bonds. We've got no non-bonding pairs on the central atom. So therefore it is non-polar. Even though all four of these bonds are polar, they all cancel each other out. You can think about it in terms of where do all those chlorines meet? Well, they meet right smack dab in the middle. So our positive charge and our negative charge both coincide in the same spot. Therefore, it is nonpolar. Okay, well, what about NH3? NH3 is also a tetrahedral, but one of those bonds is taken off. So now we have to ask ourselves, where do all these hydrogens meet? They meet down here, kind of right smack dab in the middle of all of those hydrogens. So that is the center of the positive charge. Here is the center of the negative charge. Therefore, all total, we do have a dipole moment. That is an asymmetrical molecule that is absolutely polar. Okay, well, what about BF3? BF3 should look something like this. It is a trigonal planar molecule. And again, this is just something you're going to have to get used to. There's 3 bonds. There's no non-bonding pairs. Therefore, it is non-polar. Now, one of the things you might be realizing is on these larger molecules, if there's no dots on the central atom, such as here and here, typically they are going to be symmetrical. Okay, because everything cancels out, and they're typically going to be nonpolar. In molecules where the central atom does have dots on it, they tend to be asymmetrical, and obviously then tend to be polar. Okay, there are a couple of exceptions to that, but that is a pretty general rule. If the central atom does not have any dots on it, it's pretty much going to be nonpolar because it's symmetrical. If the central atom does have dots on it, then it's going to be asymmetrical and therefore polar because those 2 dots are throwing off the symmetry of the whole molecule. Okay, one example of that, of where that doesn't apply, is right here, CH3Cl. You've got CH3, then you've got your Cl over on the side. Cl is very electronegative. This one's poling with some strength. The carbon's poling this way. This is a very asymmetrical molecule due to that chlorine being on there. Okay, so if you do have some random element that gets thrown on there, then you know that that is going to throw off the symmetry, and therefore that is definitely a polar molecule. Okay, so in general, if there's no dots on the central atom, it's going to be nonpolar. Okay, here's an exception to that. Okay, in general, if there's dots on the central atom, it's going to be asymmetrical and polar. And let me give you the only two exceptions I can think of that could possibly be on the AP exam or could affect us at all. Okay, if we look at something like XeF4. XeF4 has 4 bonding pairs. And it's got 36 electrons all total, so I've got 4 left over. So 1, 2, 3, 4. Okay, this is a square planar shape. And that shape, if you look at the fluorines, it basically, these 4 fluorines form a square. Where would they all meet? Right smack dab in the middle. These 2 electrons, 1 pair's on top, 1 pair's on bottom. Where are they going to meet? Right smack dab in the middle. Everything coincides and is a very, very symmetrical molecule that is non-polar. Okay? And then the only other one might be something like BRF3, which has that would have to be, hold on, let me think here. How about XeF2 is a good one, where you got XeF, here's 16 electrons, but I've got 22, so I need 1, 2, 3, 4, 5, 6. This is the trigonal pyramidal one that's had the whole triangle taken off, and it goes all the way back to a linear shape. So that one right there, the fluorines cancel each other out. The triangle of electrons cancel each other out. So this one is also nonpolar. So pretty much across the board, if there's dots on the central atom, it's going to be polar, unless it's a square planar shape or a linear shape. Other than that, all of the other molecules that have dots on the central atom are going to be asymmetrical. Okay, so here's just a review of those first 5. Here's HCl. We can see the chlorine is pulling stronger. It's polar. This one, again, no dots on the central atom. It's nonpolar. This one, they didn't put it, but certainly right there we have an electron pair that's pushing those electrons down, making it asymmetrical. Here's our carbon tetrachloride. That's an even distribution across. They all cancel each other out. And then here's that one with the weird chlorine on it. That definitely was asymmetrical and polar. Okay, so if you would, please take a look at these problems in the book. Look at the problems in your review packet, and then we'll go over these tomorrow.